Okay, this video is going to be on the square root of 2 and the fact that it's an irrational number. This is a very old result from way back in the days of Pythagoras and perhaps even earlier. Certainly the Pythagoreans were aware of this result, but they made great efforts to suppress it and keep it out of the mainstream knowledge. They were deeply troubled by the result, and well, that's another story. But it's an old result. It's an elementary proof. The prerequisites are minimal, as you would expect from an elementary proof, and it is a great example of proof by contradiction. One of the classic examples. In fact, I think it's probably the most famous proof by contradiction in terms of how widely known and widely taught it is. So the proof proceeds by assuming the negation of the thing we're trying to prove. So we want to prove that root 2 is irrational, so we're going to assume that it's rational, and that will lead us to a contradiction. Now the key to this whole argument turns out to be notions of evenness and oddness with respect to numbers. Now obviously even numbers are divisible by 2, odd numbers are those that have a remainder when you divide by 2. There are 4 products that you can form between the various possible even and odd combinations of numbers. So if you were multiplying 2 even numbers together, for example, you would get an even answer. If you're multiplying an even times an odd number, you would get an even number. If you're multiplying an odd times an even number, you get an even number. So you get an even number for those first 3 possibilities. The only way you can make an odd number is by multiplying an odd number by an odd number, and that will turn out to be important in this argument. So we're going to assume that root 2 is rational, which means that it can be expressed as the ratio of 2 integer numbers where a over b, where b is not 0. And additionally we're going to assume that it's simplified in lowest terms, and this relates to the even and oddness that I mentioned. So if it is simplified in lowest terms, then that necessarily implies that both a and b cannot be even. One or the other could be even, but they can't both be even. They could both be odd, and still being simplified in those terms. But if they were both even, then we could factor out a common factor of 2 from the numerator and denominator, cancel that out, and it would be further simplified, which would not meet the definition of being fully simplified. Okay, so we have a fully simplified a over b quotient, which is an expression equal to root 2. Moving on, here is our expression for root 2. It's the ratio of a to b. We don't yet know what these numbers might be, but it won't turn out to be important. We can just deal with a and b. If we square this equation, root 2 squared obviously is 2 by definition. A over b squared is a squared over b squared. And now this new equation allows us to realise that a squared must be even, because if we multiply b squared on both sides here, we have 2b squared equal to a squared, and for a squared to be equal to 2 times anything means that it's an even number no matter what b squared is. So we've learned that a squared has to be an even number, and this also forces us to conclude that a itself is even, because a squared is a times a, and if the answer is even and the two component factors are the same number, then it must be the case that a is an even times an even number. you could also form an even product with an odd times an even or an even times an odd, but the fact that it's A times itself means that it has to be the same kind of number in both instances, and therefore A must be even. So we've proven that A is an even number. We can express A as 2 times K, where K is some further integer that we haven't yet determined. But if A is even, then it must be 2 times some other integer, some smaller integer. Now we can reach a similar kind of conclusion here. So, well, first of all, let's start by plugging in the 2k for A. So we have 2k squared over B squared, and of course that can be rewritten as 2 equals 4k squared over B squared. And moving on, that would be 2b squared equals 4k squared. So clearly there's a common factor of 2 among these b and k terms, and we could cancel that off to get that b squared equals 2k squared, and at that point we've basically came full circle round to this similar argument here, where we reasoned that a squared must be even, therefore a must be even. Now we can see that b squared must be even because it is 2 times k squared, and therefore b itself must be even because for the same reason a had to be even. And therefore we've demonstrated that both A and B have to be even, which contradicts our starting assumption that we had an expression A over B written in simplest terms, because remember that forced us to conclude that both A and B can't both be even if it's fully simplified. So there is the contradiction that we've been seeking, and the only way to resolve this inconsistency is to conclude that root 2 is in fact an irrational number. It cannot be expressed as a simplified ratio of A over B, where A and B are integers, and that concludes the proof.